I want to welcome you all. Thank you for coming to my talk. What this talk is going to cover is what we like to call GIPhy, which is Google's infrastructure for everyone else. Who here is, by raise of hands, heard of containers? Yes. Who's used containers? Keep your hands up. All right, about half of that. Who here has used a scheduler-based system at work or sometime in the past, Kubernetes, Mesos? All right. So what this talk will be going through is essentially trying to contextualize why these technologies are important and what is actually interesting about them besides, new shiny. So CoreOS is a company that started with a mission, and that mission was pretty straightforward: secure the internet. And we should be done here any day, I'm pretty sure. But in all seriousness, in order to do this, there's some design patterns that we felt were necessary to implement inside of open source software and inside of systems backend computing as a whole. So with any good mission, you need a strategy. Otherwise, you'll never accomplish said mission. So we had a few different strategies that we've been taking over the last couple of years as we've been building CoreOS. The first is to separate the applications from the operating system. And I'll deep dive into how all this works later, but these are the big strategy points. The next point is to make servers extremely consistent so you understand what's running on them. The next is to tolerate machine failures. Who here would be extremely pumped if I went into your AWS console and into your data center and started powering off hosts? Would your monitoring be unhappy? Would you get people being paged? You want to make servers extremely easy to upgrade, which plays into this toleration of machine failure. And you want to simplify application upgrades overall. So we know how to make a really secure machine. It's really simple. You just ensure that it's not connected to anything else, only visual output, physical input. But this is not the world we live in today. Computers are much more interesting, and they're mostly interesting because they talk to each other, which leads to the necessity of some other things. Who here has seen this show, John Oliver's video on encryption? If you haven't seen it, it's really fabulous. If you've ever struggled to tell your family or explain to your family why encryption is important and why the federal government shouldn't be involved in encryption directly, this is a great summary. But at the end of the thing, it talked about why systems engineers care about encryption so much, and also the constant danger that we are that these encrypted systems, these secure systems that we build so we can communicate with each other, are constantly on the edge of failure. And that edge of failure is called a 0 day. And they did this great thing where they kind of try to visualize what an engineer feels like when a 0 day comes out, right? It's a disastrous moment, probably not this bad. We may feel a little strained, but not destroying hardware strained. But really, it captured this idea that with all of these systems, security is, we're constantly just a moment away from security being taken away through flaws in our software, through flaws in the designs. And they summed it up with this great saying, join us as we dance madly on the lip of the volcano. We're constantly on this edge of systems moving from secure to insecure. And so how do we actually fix this? Well, we fix this by reducing the time window from when we learn of something that's become vulnerable to when we fix it. Now, how many of you today would say that your server infrastructure, your application infrastructure, would be able to deploy a new fix within minutes? Okay. So what we're trying to do here is we're trying to move that time delta down so that instead of on days and weeks of planning, we're able to start rolling out fixes into our backend server infrastructure quickly. And we're doing this with a variety of open source technologies. Some of these are CoreOS Linux, Kubernetes, etcd, Rocket, and Docker, all of which I'll try to cover, talk about why they come together to actually create and execute on this mission. So there's 3 high-level things that we'll talk through, kind of themes of how this all comes together. The first is application packaging. Second is how to scale Linux servers, lots of them, to work together. And finally, how they work together with clustering. So Google's infrastructure for everyone else. Google has these 3 major components inside of their system. A scheduler system called Borg, Linux, obviously, the Linux kernel, the Linux user space, and then a consistent key value store called Chubby. Now, Google hasn't open sourced any of this, so what we have to do is essentially reinvent it all in open source. And these design patterns are followed by a lot of the world's largest internet brands and internet products. Facebook and Twitter follow similar patterns using different technology. And a lot of these patterns actually kind of show up inside of our mobile devices, which I'll talk about in a sec. But the reason that we want to build this style of infrastructure is to avoid single points of failure, like I said, designed for constant updates and to drive to a consistent environment. So how do we design for constant updates? The first is application packaging. So what we do today is we take a bunch of files in a package manager or maybe in a configuration management system, and we shoot those files over the file system. We kind of reboot and cringe and walk away and hope that everything works out. That's not terribly great. As we all know, there's 1,000 different things that can go wrong, and if you squint the wrong way, or if timing happens to happen in a different way, you can end up with race conditions and all sorts of mess. So what we need to do is abstract away the application from the operating system. And what this looks like is that the traditional distros have this, our traditional Linux distros have this idea that our apps kind of ride on top of this whole stack that the Linux distro maintains, from language runtimes to databases, et cetera, et cetera. And so we have this really tight coupling between the operating system and the application, which causes trouble. How many times have you really thought that it was super useful that your Python version was versioned directly with your MySQL version? This is a very difficult problem to get correct. In a lot of ways, it can be very surprising as your developers test on their laptops on Python 2.6 and then deploy into an environment running Python 3. So what we do with CoreOS, and kind of the key thing that we wanted to execute on when we built CoreOS Linux, was the idea that the operating system is very small, similar to how our Android devices and our iOS devices come with very minimal amount of stuff. They come with an app store, they come with a camera app, but then everything else is kind of installed and managed by a third-party application provider who actually understands the application and the dependencies of the application. And so this is why containers are important, is because they allow us to separate and abstract away the operating system from the app. So we manage in CoreOS Linux the base software like the kernel, an init system, some basic management functionality like SSH, and then container runtimes. Another way to think about things like CoreOS Linux is that it's a hypervisor for containers, for software that's been packaged in this way. And what containers give you is the ability to do these mixed versions, isolate the applications from each other with various isolation mechanisms, whether that be on the network or the file system, et cetera. And the user experience is pretty straightforward. You say to the container runtime or the container engine, I want to run this image that exists somewhere on the internet. I want to run this version. I may want to put these limitations around it. I may want to put it inside of this namespace or that other namespace or whatever to isolate it in various ways. But the core package management has moved away from manipulating files in the root file system to I want to run this application that has a name, download it over the internet, verify it, and run it. Now, if you're familiar with how this stuff actually comes together, what this means is that my application is packaged directly with things that I may not be an expert in. So I may package my Java runtime with my application itself. And this could be bad because I may not know when the latest Java vulnerability comes out. I've kind of moved the problem around from an operations concern to a developer concern or a DevOps concern. And so what happens when that Java vulnerability comes out or an OpenSSL vulnerability comes out and it's inside of the container that I'm deploying on my systems? There's an open source project that we've been building that we integrate into some of our products called Claire that actually cracks open these containers that you're running on top of your environment, searches the container metadata, identifies any vulnerabilities that may exist, and then explains update actions. And so you're able to say, identify, hey, I'm running an out-of-date Java, and then kick off an email or kick off a webhook to rebuild the container and ideally redeploy. Now, a scary thing about this is that we released this technology about 8 months ago or so, 8 months ago. And we found that 80% of containers today on our public registry, Quay.io, still have Heartbleed. So clearly, we are not doing a great job as a community of people building containers, actually updating them. But I think that with tooling and with automation, we can do a much better job than this. And this is why we're building this stuff as open source, so that people can automate it. And so what this looks like, Claire or whatever, is inside your dashboard. You get a breakdown of, hey, what's inside of this container? What do I need to be aware of? How do I update it? And then the other bit of containers is that we want to avoid this idea that we had inside of package management, where every package manager has their own package management system. Apt and Deb and eBuilds and whatever else have kind of been a huge pain in the butt for all of us who are actually operating systems. It's really annoying to hunt down that latest RPM dependency when you're relying on a third-party app or whatever. And so one of the things that the entire industry has been working on, Docker, ourselves, CoreOS, IBM, Google, et cetera, has been a single standard image format for packaging up these applications so that no matter where we end up, whether that be on Linux or, can't believe I'm saying this in 2016, Microsoft Windows, the same application is able to run across all those different platforms. And so we can kind of imagine a world where we end up with a single unified server packaging format. And that work is happening inside of an organization called the Open Containers Initiative, where that work just kicked off about 2 weeks ago. And it's looking really good, hoping to get it out the door in the next few months. All right, so the next bit of this story is how we actually run these operating systems. We figured out a way of decoupling the operating system from the app, but the operating system itself can also change. So right now, patching the operating system is difficult. The kernel is also pretty difficult as well. If we break a dependency inside of our operating system, it can be really annoying because every time we want to do a security update to that underlying operating system, we also have to retest every single application, even if that application didn't necessarily directly depend on that thing. And then there's the uptime risk of if we update, do an apt-get update and reboot, that we may lose whatever applications we're running on there, and we have no way of actually protecting against that uptime risk. All right, so inside of CoreOS, we kind of redrew these lines, and what we did was we took inspiration from the web browsers, which, as you remember, a while back, probably about 12 years ago, a lot of times what would happen is security vulnerability would come out, and then you'd get this dialog box where you had to click next like 14 times, and then type in your admin password, and then the browser would install its update, and then you'd reboot your browser. And then Chrome came out about 6 years ago and said, forget all that, we know how to manage the updates to our browser. And Internet Explorer and Firefox came along for that same ride of automating the browser updates. And as a bonus, we got probably one of the most secure front-end internets that we've ever had, because as soon as security vulnerability comes out, we have some confidence that the vendors will actually push those updates instead of relying on humans to click next 14 times. And then we also got new features. We got new features like HTML5, which was, I believe, delivered to the front end in a wide way several years, I think a decade ahead of what the expectation was. So we got more security and a more feature-rich web. And so in a similar way, CoreOS does an atomic operating system upgrade. So by default, CoreOS will get a stream of updates from our public, freely accessible update servers. Those updates will be downloaded to the inactive partition. CoreOS has an A and B partition at any time. So while you're running the A partition, we in the background are updating the B partition. This means that at no time is your operating system in an inconsistent state. You're either fully running the A version or you're fully running the B version of CoreOS. We don't have this, oh, libc was removed for a half a second and then my application couldn't launch sort of problems that we have inside of traditional package management systems. All right, so that solves the concern of the individual OS. And the last bit is clustering. So clustering is actually a fairly complex topic, as you can imagine. But the field, the entire open source industry has kind of come around to a few different best practices around this. And we've chosen a few ourselves. So we'll kind of talk through what's important here. So the reason that we want to do clustering is to maintain and manage this uptime risk, that if we are doing these atomic updates, that means that an individual machine inside of our data center may take downtime, and it may take downtime regularly, and that's okay. And it's not annoying on our phones. It's not annoying for an individual to have their phone for 5 minutes reboot, but it is pretty annoying if that's where your application server was that's serving the homepage of your company. If that individual server goes down and you're serving 500s, you're going to probably get paged and have a pretty bad day. And so you need clustering in order to manage this uptime risk. So we know what an operator's paradise looks like. It's really easy to scale out the application. It's really painless to upgrade those applications. And we have an extreme tolerance for individual machine failure. The if I unplug a computer, are you happy test. And what it looks like as a block diagram is that we have several machines, these little white boxes, and we have these applications running on these white boxes. And we have some sort of metric of health, which is whether the service is actually responding, and then some capacity for that application, so number of requests that it can handle per second. And so the idea is that we could just plug in more racks of servers, and that our clustering system takes care of taking advantage of that additional capacity, which then gives our applications additional capacity. And we think less about, well, how many gigabytes of RAM and what sort of CPU is running, and more about, well, how many application requests can we handle, taking that point of view from infrastructure to application. And if we lose a single machine, we're not thinking about that single machine, we're thinking about what is the capacity that we lost. Perhaps we can schedule a duplicate, double schedule the application to a single machine, that sort of stuff. All right. And you'll notice that through this entire scale up, scale down, the application remained healthy. This is sort of what you want, what we all kind of want to achieve, and what we've spent, probably every project that I've ever been on spends the first 4 months doing a Chef pipeline, a Jenkins pipeline, figuring out, automating our F5 load balancers, adding and removing stuff from ELBs, what this looks like. I'm sure we've all had similar experiences, right? The automation of this stuff is not something that we generally take off the shelf for every new project. All right, and then the next concern is that we actually want to think about upgrading these applications. So decommissioning a single instance, we lose some capacity, replacing it with a version 2 that fixes a bug or fixes a vulnerability or whatever, and being able to do this in an automated fashion, hopefully all API driven, and in a way that we are thinking less and less about doing this regularly inside of our environments. All right, so this obviously calls for some sort of level of coordination. We can't do this ourselves as good as most of us are at bash scripting or something like that. It's not going to get you very far in these systems. And the reason is because we're actually designing these systems to be tolerant to machine failure, and even our laptops, a single machine, shouldn't be the single point of failure in order for us to be able to do these sorts of operations. So you need cluster coordination for doing things like leader election, cluster-wide locking or semaphores, dynamic reconfiguration of applications, so that you can say this new certificate authority needs to be used, et cetera, and that rolls out dynamically to the cluster, and for service discovery and load balancing. And these things need to happen in a way that are tolerant to individual machine failure. So designing something like this with these properties is a really difficult computer science problem. And Google has solved this for themselves using a system called Chubby. There's a great white paper that describes the system. Unfortunately, we don't have that system, so we have had to build something ourselves. And so we built a consistent, highly available key value store called etcd, which holds on to this really important cluster configuration information and tolerates machine failure. So hopefully if the Wi-Fi holds up, I can avoid doing this screenshot demo, but let's see. So, okay, cool. So this is a demonstration of etcd. This is a live etcd cluster that's running on some virtual machines in Google Compute, and a visualization of these machines. So etcd has, in this case, configured for 5 machines, and it's able to, in this configuration, tolerate 2 machine failures. Systems like etcd are essentially like computers playing democracy. And so at any given time, you need a simple majority of the machines to be up in order to actually vote and move forward with decisions in the cluster. Now the decisions are going to be things like where is my load balancer, where should I schedule this work, etc. But for the purposes of demos, we will put important information in here like foo is equal to bar. And what will happen, I'll submit this information to the cluster, and you'll notice that the hash of the cluster changes. And this is going into a key value store. And this just is a simple roll-up of all the data into a hash. Now, the interesting thing about etcd is that this right here, this green dot, is the leader. So it's the one who's actually ensuring that everyone replicates the data and takes care of it. Now, etcd, what it can do is it can tolerate individual machine failure, including the leader failing. So what will happen, this is all slowed down. This happens on the order of milliseconds, but it's slowed down so humans can understand what's happening. But what happens is after I kill that machine, a new leader is elected through voting. Again, they're simulating democracy. And I'm able to continue to use the key store. So I'm able to submit new keys to it. I'm able to get keys back out of it. And it continues to work. Okay? Now, what happens if I restart this machine, say it upgrades from an operating system update, is that it will come back online, it will get a replicated version of all the data, and it'll get caught up to the latest version of the cluster information. And it looks like there are 6 users on here right now, and it looks like somebody else is giving this exact same demonstration, so somebody else just killed one of the members. But you'll notice that the cluster continues to operate as expected. So this is what etcd is designed to do. Hold on to key values that are really important, ensure those key values remain right and read available in the face of machine failure. All right, any questions there? Good. All right, so we built etcd from scratch starting about 3 years ago. The reason that we built it, there are existing systems that have these similar properties, the most notable of which is called Zookeeper. But Zookeeper has a few problems, and we wanted to address those problems directly. One of which is that it isn't very cloud native, for lack of a better term. It's really difficult to reconfigure the system dynamically at runtime. etcd, nearly everything can be configured at runtime, so you're able to add and remove members from the cluster. You're able to pass off leaders from one to the other. Say that a leader receives sig term. We're able to pass off the leader without taking a downtime, or not downtime, but taking a longer latency. So it essentially is transparent to the clients. It looks like a small sub-millisecond blip. We wanted to use very familiar APIs for developers, HTTP and JSON. And so we built this system essentially trying to lower the barrier to people getting into these sorts of systems. And like I said, it's a very simple key value store, and that's the primary API into it. And then the other thing that etcd allows you to do is watch changes across the cluster. Now, when you're maintaining maybe dozens or hundreds or thousands of machines, you really want machines to be able to get notified of when changes happen almost immediately. And so etcd essentially gives you a way to stream and keep an eye on everything that's happening inside the etcd store and notify and essentially do webhooks and make the system very dynamic, which we'll show later in the demonstration. All right, so a number of applications are built on top of etcd. etcd really does nothing except for hold on to key values and then allow for atomic operations on those key values across the network system. And so with these two primitives, a lot of different systems are built on top. We have a thing called Locksmith, which controls the rollout of updates across the CoreOS cluster. So no more than n number of machines are rebooting at a time. So you can plan for capacity planning of getting those stream of automated updates. Service discovery systems like VulcanD and SkyDNS are built on top of etcd. VulcanD is a dynamically configured HTTP and TCP load balancer out of a company called Mailgun, part of Rackspace. And then SkyDNS is a DNS server able to serve up authoritative and recursive DNS. And then cluster orchestration systems such as Kubernetes, which I will talk about in depth here in a moment, and Cloud Foundry both use etcd. And there's a lot of other industry adoption too. There's about 500 other projects on GitHub using etcd, and a number of other projects that use etcd in various capacities, including Deis and Docker and a bunch of others. All right. So who here has heard of Kubernetes at all? Awesome. Who's used it? Who's played with kubectl? All right. So what I'll do here is walk you through what Kubernetes is, why it's important, how it's not terribly different from what we're doing today, and then hopefully leave you with some instructions to try it out on your laptops. So again, we'll go back to this diagram. What Kubernetes allows us to do and helps us do is deploy these rollouts and manage these resources of lots of machines and the actual applications running on them. What I'm going to be going through here is some guides that you can find at coreos.com/Kubernetes. Actually, let's just go ahead and do that. So what I'm going to be doing is running a cluster on my laptop. If you want to actually get started, go up to the documentation section here on coreos.com. There's a Kubernetes section. Go down here, and there is a single machine Vagrant setup here. And so if you're familiar with Vagrant, this will set up in pretty straightforward, about 5 minutes. You'll have everything you need to start running Kubernetes inside of a single virtual machine on CoreOS. And it runs on OS X and Linux, and I believe Windows 2. Yep, it does. So you should be able to get it up and running somewhere. So I'll be using those instructions here. We have other instructions there for running Kubernetes on top of AWS and other environments as well, bare metal, et cetera. So the first bit of Kubernetes that's interesting is the idea of a scheduler. And scheduler is about getting work to servers. So we've all probably built our own scheduler. It's this scheduler. I think we're all familiar with it, where you write some sort of application, you scopy it into /opt, and then you SSH into the machine and you run that application. Who here's used systemd run? Oh my goodness. Who here has run an application in Screen or Tmux before in production? Okay, systemd run is for you. We're going to take a small detour. We're going to learn about some new system administration stuff. One thing that systemd is faulted for is having way too much stuff. The one thing that systemd does extremely well is it adds a bunch of best practices that really are long overdue inside of Linux. So what I'm going to do is SSH into this machine that I'm running that we're going to be doing the rest of the demos on. But what systemd run does is it allows you to take a set of command line flags or a set of command line flags that you would have ran in your terminal and just run them inside of a systemd service. So I'll do something like really important like sleep 5000. And then what this actually does is it spawns off a real systemd service. So like something that's actually monitored by a process, an init system, and actually logs to like a logging system. All these things that Screen doesn't do at all. And so if you do systemctl status, what you'll find is that it's active and running, and that it's currently executing bin sleep and sleeping for 5,000. And we're able to do all the normal stuff that we would have done if we had written an init file, a service file inside of systemd, like stop it or tail its logs. Of course, the logs of sleep are not very interesting, but you get the idea. I'm able to put isolation around it, say it's only allowed 1 gig of memory. It doesn't inherit my entire environment, like my AWS secret keys that I might have had before running screen, et cetera. So if you learn nothing else from this discussion today, please never again run anything in screen ever, and use systemd run. And luckily, systemd is in every operating system today, whether you like it or not, so you'll get it for free. All right, so we've written these schedulers, so we're able to copy things over and then just kind of say launch it. So this is the scheduler we all are familiar with today. We may have gotten really fancy, chosen something like Capistrano or Fabric or something like that, where we essentially have a tool that does a gigantic for loop for us. And what that does is it, in a Python application running on our laptop, kind of goes through a set of machines and deploys. Or we may have gotten really fancy, and we may have a certain set of machines that have a GPU on them, and we need to deploy an application just particularly to those servers. And so these are the ideas of a scheduler. And these are things that Kubernetes does natively. You're able to tag machines with certain properties. It takes care of making sure that work that you want done lands on those machines. And then it does something even more important, which is the scheduler and the Kubernetes API takes care of driving the cluster state to your desired state. So there's this idea of a replication controller inside of Kubernetes. And the replication controller and the scheduler kind of work together. So inside of a replication controller, I describe the system I actually want running. So I say, my production web application, I want one replica of that running. Okay? And so the replication controller, essentially working with the scheduler, says, well, shoot, there's 3 of them running right now. What do I do? And so what the Kubernetes does and what the scheduler and the whole system do is they drive the state to you, the human being's desired state. So it drives the state to 1. Similarly, if you want to scale the application up, drive it up to 5. It works just like a thermostat. So I have an API way of saying, not only do I want to deploy this application, but I want these certain properties of this application. So I want being able to handle this number of requests per second. And I want the scheduler and the system to take care of handling that for me, even in the face of machine failure. So if one of these goes away because a machine failed, the scheduling system will actually continue to drive the state forward. And then the last thing that Kubernetes does is it helps with service discovery and adding and removing things from load balancers and DNS entries. Okay, so Kubernetes has this really flexible system called labels. And so what labels are able to do is say, I have these applications. Pods essentially are running instances of applications. It's like a pod of whales. You can have multiple processes running in a pod. And so you label these things with information. Say I have a pod that's running with labels saying environment equals dev and app equals web, similar for test and prod. And you're able to do things where you tell your load balancer, I want to take these things that are labeled in this way and put them behind different load balancers. So a very common pattern is that we want to have, say, test.example.com, which is firewalled off from the rest of the internet, but which our developers use to test out the latest release of master. Beta.example.com, which is a combination of our current production application and the application that we intend to roll out here in the next few minutes or the next few hours, and then the actual production workload. And you're able to, essentially using this language of label queries, say, I want a load balancer that contains these applications. I want a second load balancer that contains these applications. And it all happens dynamically as things are added and removed from the cluster. All right. So what we'll do now is actually start to walk through some demonstrations of how Kubernetes works in production, or actually works in these sorts of environments. And what I have set up already is that single Vagrant cluster. So what I did before this was I ran Vagrant up and got the latest version of Kubernetes and everything up and running on this machine. That process takes about 10 minutes and looks like an empty prompt with no log lines. So I'm going to skip that part, do a little cook ahead thing, and we'll start to just look through how applications are deployed. Okay, so the first thing that I'm going to do is deploy a service on top of this cluster called the Tectonic Console. The Tectonic Console is something that you're able to get from tectonic.com. We have a freely available version of it called Tectonic Starter. You can read the instructions. You can get it running in about a minute. But I'm going to do a couple interesting things with the console here to kind of talk through why this stuff works the way it does. Okay, so the first thing that I did, shoot, sorry you missed that. The first thing I did was create a thing called the console service. And what the console service is going to do is expose a port on top of my virtual machine that load balances the console. And it's going to be running on this IP, which is my virtual machine. I haven't actually deployed the console yet, so this load balancer is just holding onto my connection until I deploy something. All right. So the next bit that we're going to do is actually deploy the container. In this case, we're going to be actually deploying a replication controller that's going to deploy 2 copies of this application. Oops. Keep doing that. All right. So what this does is it deploys a replication controller called Tectonic Console v014, which is the current version, well, actually the previous version, and puts that inside of the cluster. So if I go over here, what should actually happen is I get a copy of the Tectonic Console up and running. And the interesting thing here is that we can look inside of the console, and we're actually running the console on top of Kubernetes itself. So this is me looking at a load balancer coming from Kubernetes that's introspecting Kubernetes. And so what we have here is the Tectonic Console service. This is the actual load balancer, the IP address of that load balancer. Underneath it is the label query, the actual query that finds and puts all the applications behind this load balancer is Tectonic app equals console, and it finds these 2 applications. And so I can drill down and say, okay, this is one of the actual running processes. What image is it coming from? What machine is it running on? What version of, that's completely incorrect. That's weird. So we just rolled out Kubernetes v1.2 into CoreOS recently. And one of the weird bugs is that it identifies CoreOS as Debian. So we'll have to track that one down. But it identifies the machine. You can find its IP address, the kernel version, which you can see is clearly CoreOS kernel version. In any case, so it gets all the machine information, et cetera. So this service is running these 2 applications. We can find the replication controller for this service here, and you're able to do things like, say, change the desired count from 2 to 3. And you'll see that really quickly a new copy of the application is launched, goes from pending to running, and we have now 3 copies of the application running behind the load balancer. And then if I was to, say, delete this pod, maybe I was unhappy with it or it was running on another machine, yes, what will happen is that immediately the scheduler will find, oh shoot, the desired count has been moved from, or one of the pods has died. In this case, it was because of human action. It could have been because of some other action, and it actually schedules a new pod to replace it. All right. So that's the Tectonic Console. Now, the next thing that I want to do is actually start to do a rolling update of this. So move from v1.04, whatever we're running, to 1.5. And so the next step here is to do. Well, I'll run this little bash script, and this little bash script is going to do a while loop, sleeping for a second, checking the JSON endpoint that we have that identifies the version of the console that's running, because refreshing a page and showing you a slightly different font size is not going to be terribly interesting. And so what we'll do now is actually start a rolling update process of the Tectonic Console. And kubectl has this thing called rolling update, and what it will do is it'll drive the existing replication controller, the thing that's actually pushing state, and drive that thing to the new version. So I'll come over here and run that command. And I've said to have the update period of 5 seconds, and what it's going to do is check the health of the new service and the old service, and start to add new copies of the application running the latest version, and then remove copies of the application that are running the old version. And so what will happen here in a few seconds is that we'll start to see new copies show up. There you go. that are running v1.5, and you'll start to see the number of responses that we get running 1.4 disappear until the actual rollout's complete. So you'll see that it's kind of doing this back and forth of removing one copy of the old one, adding a new copy, and then at the end, it will completely remove all copies of v1.4, and we'll end up with a cluster that only has the v1.5 version. And this is all kind of automated and doing health checks of the actual services as they go. So with any luck, if I come in here, sure enough, I see that v1.5 is the version that I'm running of the console. And as a bonus, I get, where's the new feature? I get the new manage namespaces feature inside of the console as well. So I'm able to manage these namespaces. Cool. All right, so that's a pretty straightforward application. It's completely stateless. It's very easy to model because there's only one single process, and that process is behind a load balancer. What we'll do next is actually look at a slightly more complex application and see how those applications get modeled, where there's probably 3 tiers. There's the load balancer tier, the application tier, and the database tier. Any questions on this so far? Is everybody following along? Good? All right. So what we'll do next is we'll go into the actual Kubernetes code base. In the Kubernetes code base, there are a number of examples. The example that I'm going to be using is a really simple one called guestbook. And the guestbook has a number of different tiers. The first is that there's a set of Redis configurations. And now Redis essentially is, if you're not familiar, it's a database. And Redis is going to be ran similar to a stateless application. We're going to have a number of replicas. Those replicas are going to be then put behind a load balancer, and the actual web application is going to talk to that load balancer to find Redis. And so you'll see here that the actual configuration of this stuff includes the image. It includes metadata about the actual ports that service is going to be listening on. It includes details like how am I going to actually label this pod so that it can be put behind a load balancer, et cetera. And then it's going to describe the actual number of replicas that we are running. In this case, we're going to be running a single replica of master and lots of replicas of the worker or slave machines. So the next bit is the actual load balancer. So the load balancer for the master is going to load balance the port, the Redis port. It's going to be selecting for things that are called app Redis and role master. And then similarly, we're going to have the slave controller and the slave service that load balance and control those things. The next bit of the application, that's the database tier. The next bit of the application is the controller for the web app itself. What we're going to have here is 3 copies of that application. It's going to be running an image called guestbook, and it's going to be putting it behind container port 3000. And then the last interesting thing is this service. The service describes the load balancer, and one thing that I'm going to be tweaking here in the examples is adding this thing called the node port. A node port is a convenience so that I'm able to hit a well-known port on top of the VM to actually hit this application. So I'm going to hit the well-known port of 3152. And this is similar to what we do today for load balancing and service discovery. We probably all have that Excel spreadsheet that says, port 9007 is this application, port 9008 is this other application, maybe secured with TLS, et cetera. So it's just taking that same idea, only we have this load balancer in the middle. So we'll write a really simple for loop that's going to submit all of these configurations into the cluster. And so it will just submit all the work, and then the cluster will sort it out. This is sort of different than configuration management, where we think of things from top-down recipes. Because Kubernetes has this idea of this thermostat, this replication controller, this driving state, kind of built throughout the entire thing, you can just deploy a bunch of stuff, and the cluster will eventually figure it out. So, woohoo. So what I'm running here is if you want to go to philly.ngrok.io, you can actually hit this service. ngrok is this great thing, if you're not familiar with it, where it's this load balancer that's in the cloud. And that load balancer, I actually tunnel out to it. So if you hit this load balancer, what will happen is you're actually hitting this load balancer running in AWS somewhere, and then going over this reverse tunnel to my laptop over the conference Wi-Fi, and then displaying the actual guestbook messages on this website. So in any case, since none of you are getting involved, I'm going to enter my own guestbook information. Hey, Matt. Don't put anything inappropriate in there. This is being recorded. And so this is actually the running application. And say that I'm just getting super overwhelmed with just how much traffic I'm hitting on the guestbook. Or actually, in this case, I'm getting super underwhelmed with all the traffic I'm getting. I'm going to just scale down that application because Wawa is probably not the most important thing. Wow, Nomad project, aggressive. All right, so that's kind of how, thanks everybody. Did I mention that we're using Redis? All right, so I'll let that keep running. I'll wait for the cat memes to show up here. It should be any second. So that's kind of a simple demonstration of why this technology is powerful and how it can be used in production. So there's some other things that can be done here. So you could perhaps start to do things like load balancing one copy of your application versus the other, and then moving that workload over. Say that you want to just roll out to a set number of users, so you can actually start to do things like, say, only 1% of our users see the new version of the application, et cetera. There's lots that can be done with all of this technology, but simply to say that most of this technology is built to map to almost all the existing use cases that we have for load balancing and service discovery and scheduling of applications. Now, there's a lot of new stuff that's happening upstream in Kubernetes, one of which is a thing that we're introducing called Rocketnetes. Rocket is a container engine that we built with security and some other properties around how these applications are actually ran. That's different from container engines like Docker. That's going upstream here on the next release, Kubernetes v1.3. We've been adding things like authorization and authentication using OIDC. If you're not familiar with OIDC, it's what powers things like Facebook's login or GitHub's login or Google's login. So you'll imagine a world where you can actually start to share these clusters with people who are on your GitHub team or inside of your Google organization. And then doing other things like ensuring that there's end-to-end security between the cluster's controller and all the cluster workers, and doing that in an automated way, because there's probably about 2 of us in the room who have ever successfully operated a certificate authority. I'm certainly not one of them. I know that many people have not actually done this successfully, and we want this to be done in an automated way. And then one last bit is that for whatever reason, Kubernetes was beat up for a little bit for not scaling well. And this was because it only scaled to around 200 machines as of about 9 months ago. And I would argue that most of us aren't managing more than 200 machines per application per failure domain anyways. But we've greatly improved that. Kubernetes now easily scales to 1,000 machines. If you have more than 1,000 machines, we'll probably 10x that again in the next release. You have more than 10,000 machines, I'd really like to discuss to you the concept of failure domains after the talk, because that's getting a little out of hand, having one single cluster control more than 10,000 machines. Nobody I've heard of, like Google or Facebook, does this in production. They have separate failure domains for large sets of machines. In any case, Kubernetes is beginning to scale very, very well, running 30,000 applications on top of 1,000 nodes in the most recent release. All right, so this overall story comes together through a combination of 3 things: a change in how we package applications for our servers, changing how we actually operate Linux operating systems and how we can do that at scale with consistency, and bringing it all together with clustering. So this all sounds great. Is anyone successful with this in prod? This is probably the last question that you're all thinking. So we have a lot of folks that are using this in production. International Securities Exchange is a publicly traded options exchange. They talked about using containers in CoreOS at a recent conference we held in New York City called Tectonic Summit. They're running this on bare metal. They have a low latency trading platform. They have billions of transactions a day and 150 million requests per second, all using containers on top of CoreOS. We have a number of other well-known brands and folks using these technologies. Viacom, Salesforce, and Verizon are among some of them. There's lots and lots more. We have a few case studies on CoreOS.com and Tectonic.com if you're interested in how these folks are using it. So our mission is to secure the internet. We're doing that through separating applications from the operating system, making servers extremely consistent, building systems that tolerate individual machine failure, making the individual server easy to upgrade, and simplifying those application upgrades so that we lower that time from when we find a bug or we find a security vulnerability to when we actually are able to deploy it and get it into production. And of course, all this technology has the knock-on effects of making our lives as operators, as people developing applications, a lot easier. And that is a secondary effect of just simply automating as much of this as possible. So what we're trying to avoid is this, and I think that we're on a good path to doing that. If you want to fly to Berlin, we have a conference in Berlin, May 9th and 10th, called CoreOS Fest, where we'll be talking about all these technologies and meeting with folks that are building them. If you're interested in a commercial distribution of this stuff, you can find it at tectonic.com. If you are in the New York area and you are interested in a job, we have a team in New York that builds this product called Quay. Quay helps you build and store and distribute containers. You can think of it as essentially a storage and CI system where you might have used an FTP server for storing your apt or RPM repos. Quay holds onto your container repos. And with that, I want to thank you for your attention. I'll take some questions, and that'll be that. Thanks. We have a mic too, so raise your hand and the mic will run over to you.
Just a kind of a detailed question on Kubernetes and the load balancer.
Yep.
Does the load balancer terminate SSL? And if it does, how easy is it to go in and tweak, for example, ciphers and SSL ops that obviously will be changing as the security things happen in the real world that you have to react to?
Yeah, great question. The load balancer that I was using is an IP tables-based simple load balancer. What a lot of people do who want to terminate SSL is they deploy Nginx or something else in the middle. And I would recommend that. Nginx is a pretty battle-hardened load balancer. You can also deploy HA proxy and that sort of stuff. So what that looks like is that you have the IP tables load balancer. That IP tables load balancer then hits your TLS termination layer, and then the TLS termination layer reverse proxies to your application tier. And there's recipes in there in that examples folder in the Kubernetes code base that show you how to run Nginx in a SSL termination mode. Yep. Great question.
In large-scale CoreOS deployments, what do you see folks use in terms of provisioning and deploying the VMs that the containers get deployed into?
Yeah. So what we've seen is kind of all over the map. We have folks we have tooling like kubeAWS that actually just works directly with your cloud providers. It's essentially, we'll be building more of those specific toolings around different cloud providers, OpenStack and Azure and Google Compute, et cetera. So that tooling is fine. Really any tooling that can spin up a VM works fine. The only complicated part of setting up Kubernetes is the control cluster. The worker machines can be scaled up and down really simply using whatever tooling. And we actually have a lot of stuff that we're going to be doing in Kubernetes v1.3 to make the control cluster even easier to spin up. We have this idea of a boot Kubernetes. So we're actually using Kubernetes to bootstrap Kubernetes. And I'd love to talk about that stuff offline. It's kind of cool. We SSH in from your laptop to a bunch of hosts, and we launch a Kubernetes that's running on your laptop. Then the machines, these virtual machines, bootstrap themselves into becoming the control cluster. But essentially any tooling can do for deploying this stuff. Any other questions?
So is Fleet kind of dead long term? I mean, is the idea that Kubernetes on CoreOS would become integrated and then you would just use Rocket to replicate that functionality?
Yeah, so for those who aren't familiar, Fleet was a project that we created about 2 years ago. Fleet is a scheduler system that's based on top of systemd. So Fleet essentially is continuing with maintenance mode patches. So we have a team that is increasing the scale of Fleet because we have a number of production users who are using Fleet and fixing various bugs, known issues. We hope to have a new release of Fleet out with a lot of that work done in the next probably month and a half. And so Fleet is not dead, but it's essentially in maintenance mode. And what happened was that we built Fleet about 4 months before Kubernetes was released. And then Kubernetes was released, and it's like when you start writing something and then somebody like completes your sentence or writes the entire blog post for you. That's essentially what happened with Fleet. We had a bunch of ambitions, and those ambitions were pretty clearly being accomplished inside the Kubernetes project. So we've joined the Kubernetes project and have become big upstream participants in that project. And the tech stack is very similar to Kubernetes. Is learning how to talk to systemd through our Rocketnetes work. It uses etcd as its cluster and configuration store. And so it worked out that way. But we do have, like I said, a ton of people using Fleet in hundreds and thousands of machine clusters with success. It's just we won't be continuing to add features. All right. Well, if you have any other questions or you want stickers, come meet me at the podium for a couple minutes, and thanks again.